Hello, everyone. I'm Samy, and I'm speaking from Fortaleza right now. It's just morning here. It's very early for me, but um, we'll move on as expected. And on a quick disclaimer about this work, just to situate what we do, we situate this work as in a series of other works where we investigate semantic correspondences between augmentation systems. Um, for us, we can see some results on this even on Dong's paper and some other papers before. In logic programming literature, they are very common. Every time someone would propose a new semantics, they would compare to the previous ones. So, but involving different semantics and systems, the method we use, at least, it started with Winning Wu, who was advised by Martin Caminada, and we did some works with Martin. And well, we've investigated in connections with logic programming. We looked into abstract augmentation and ABA. We looked at a little bit at SETAF with logic programming and ADFs with logic programming. Now we're looking specifically into SETAF and ADFs. So in all of these works, all we do to compare the expressiveness or expressivity of the systems, we consider translations between the theories in each system and possibly translations between the models of the different systems. Of course, in augmentation semantics and in most augmentation systems, we'll call those models extensions or labelings or something like that. But in the end, if you look at a bigger picture on the sense of logics, we can just consider interpretations and models, right? So here we'll be talking indirectly about extensions, both in SETAFs and ADFs. I will avoid some details about the semantics. We'll mostly look about what the SETAFs are, what the ADFs are, and how we translate the theories in each system, because the results follow directly from the translations in these cases. We can get coincidences between usually you have to have some kind of mapping between the models of matching theories. And in this case, we just get an absolute coincidence of semantics in all the semantics we could consider. So both SETAFs and ADFs and abstract dialectical frameworks, they extend Dong's abstract augmentation frameworks in some way. So when we look at abstract augmentation, they are just a pair of arguments, a set of arguments with a binary relation between those arguments, which express attacks between the arguments. And as most of you in the session know, the attack relation intuitively expresses that an argument should be accepted only if all of its attackers are not accepted, if all the attackers are rejected. Then when we go to SETAFs, which are frameworks with sets of attacking arguments, the idea is to expand the concept of abstract augmentation frameworks by allowing sets of arguments to attack instead of just singleton arguments, right? And the intuition here is that in some situations, individual arguments may not be enough to defeat a different argument, but when jointly attacked with other arguments, they could be strong enough for the defeat. And the concept doesn't change much in the way that we write them. We just get that in the relation, in the attack relation, the first parameter of each pair will be a set of arguments instead of a singleton argument. And the drawing of the framework changes a little bit because we'll have those joining arrows to say that, for instance, here, arguments A and D jointly attack argument C. And in general, for the semantics, it's pretty much the same idea. An argument will be accepted if none of its attackers, which are now sets of arguments, are rejected. That's pretty much the same idea. And for a set of arguments to succeed in the attack, they need to be both accepted. Now, when we move to ADFs, it gets a little more complex in a way that we don't draw the abstract dialectical framework, because the relations between the arguments can be very complex. The generalization that abstract dialectical frameworks propose for those frameworks is that they allow us to express acceptance conditions for each argument, and those acceptance conditions, they consider all the possibilities that according to acceptance or rejection of linked arguments, which are here called statements. And in the main definition, we use this here. We consider the parents of a statement or those other statements that have links to it. It could be a self-link, but we don't really call them attacks or supports. We just call them links. And an acceptance condition will consider all the subsets, right? The power set of the parents of S, of the statement S, and map them to true and false. So for a brief example, we could have on our an ADF with three arguments, with three statements A, B, and C, where the links would be just BA and CA, which means B and C are both linked to A in influential position. B can influence A, C can influence A, not the other way around. So the parents of B and C are empty, the parents of A are B and C. And we see here that for the acceptance conditions of B and C, we just get, this could be false as well, right? This is just an example, but the only subset is the empty set. So this is more straightforward to show, and they could be true or false. In the case that this was false, the argument could never be accepted. But for A, we should consider, at least at first, all the subsets of its set of parents. And the values here is just an example, but there is a reason why I placed this one as false and the others as true to motivate what we are going to do. And moving further on those intuitions, we can actually just express those sets where the acceptance condition will lead to the acceptance of the argument, because the other information where they would become false is redundant. And those acceptance conditions, as Jesse showed before, can also be expressed as propositional formulas. I'll not use the propositional formulas because I consider for this presentation, the sets of conditions will do a better job for us for the connections that I want to show you. So I just moved up a little bit, right, to focus on the example and show something that is happening here. So if you see, the set BC will cause A to be rejected, while the sets of B and the sets of C alone would allow A to be accepted. So in this particular example, what we have is that the sets that just have B and the set that just have C are maximal sets for which A is accepted, while the set that has B and C together is a minimal set for which A is rejected. And in a way, what this is modeling is precisely what we see in SETAFs. This is the situation where B or C are individually not enough to defeat A, but together they are enough to defeat A. And this is the kind of things that we'll see when we start to study the connections between SETAF and ADFs. That's precisely what will happen. the connections between SETAFs and ADFs were already studied in one direction, right? With a translation from SETAFs to ADFs in a paper by Sylvia Poberg in 2016. The translation, it gets, if you notice that we use the same set A, both in the SETAF and in the resulting ADF. So it means that every argument in the SETAF will become a statement in the resulting ADF. Then we just need to tell what the links and the acceptance conditions will be. So the links will be any argument from the SETAF will be in a link in the ADF if it is in any of the sets that attack. For argument A, in this case, when it becomes a statement in the ADF, for each set that attacks A, all of its elements will have a link to A in the resulting ADF, right? And for the acceptance conditions, what we do pretty much is to say that for each subset of the parents of A, the result will be to reject argument A if any of its subsets, if there's any of its subsets, maybe there's something missing here. Oh, okay, so R is from the SETAF, so that's it. If any of its subsets is actually a set attacking A in the original SETAF. Otherwise, it will be true. So what we see coming from this translation in the resulting ADFs that we get from the translation is precisely what I was showing in the previous example. If a certain set is enough to reject on the argument A, for instance, the statement A in the resulting ADF, then every superset of B will also need to cause the rejection of A. On the other hand, if a set of links in the ADF would cause A to be accepted, to be true, then all of its subsets need also to cause A to be true. This is not general for ADFs. This is something that happens in the resulting ADFs from the translation by Poberg. Okay, so again, we see here that some of the conditions, they will map they will model minimal rejection conditions for the targets of an attack in the original SETAF in this resulting ADF. Now, with this translation, it can be shown that this result is in a serious paper, that the complete semantics of the resulting ADF coincides exactly with the complete semantics of the original SETAF. Since this is a coincidence, we can generalize this to the particular cases of the complete semantics, such as the preferred semantics, the grounded semantics, and so on. Now, on our work, what we do is to look the other way around. We are interested in checking if SETAF somehow also captures ADFs, or at least what fragment of ADFs would correspond to SETAF. And in our efforts, while we're looking at this, we were drawn to this fragment, which is called attacking ADFs. In the literature for ADFs, most commonly we'll be talking about bipolar ADFs. This is the most widely mentioned, which is also based on this definition. So attacking ADFs are a little bit more restricted than bipolar ADFs, because bipolar ADFs are those where each leak is either attacking or supporting. If I remember correctly, they cannot be both at the same time. In general ADFs, they can. these two concepts of supporting links and attacking links, they are not mutually exclusive. They can happen at the same time for a link. And a link indeed is supporting if we must be looking at the statement S, right? And we must have for no subset of the parents of S, we cannot have, right, for no or in the subsets of S, in the parents of S, we cannot have a situation where or accepts T, accepts S, and then when we add in another argument or, S will be falsified. So this is what a supporting link is. Intuitively, this means that or is a supporting link in D if it never causes by itself the difference to make a statement be rejected. It is not the tipping point to make the statement become rejected. And a link is attacking, it's the dual concept. Similarly, if the link is never, if the statement is not the tipping point to make some other statement become accepted, which means that if it should be rejected somehow, adding this link to the condition will still make it continue to be rejected. It will never be the tipping point to make it be accepted. And depending on the way that we specify the acceptance conditions, some statements can be at the same time, some links can be at the same time supporting and attacking. This could happen in an ADF. So an attacking ADF is one where every link is attacking in D. This does not exclude the option that it could be supporting. In these cases, we say that the link is redundant. Overall, the name is redundant because we can get rid of them. We can simplify. If we detect that a link is redundant, we can just remove it from the ADF. There are procedures to do that. When we have an attacking ADF, in particular, we get again those minimal rejection conditions. That's one of the consequences of having only attacking of all links in the ADF being attacking links. And this is something that I highlighted on Polberg's translation. So we also had some special interest in this class of ADFs, which are the attacking ADFs, when we were studying semantic connections between ADFs and logic programming in a previous paper. We have several results and correspondence results that would hold perfectly for ADF+. Based on those observations, what we do first, that we noticed and proved that Polberg's translation, that the results, the ADFs that are obtained from this translation are necessarily attacking ADFs with no redundant links, which is a quite restricted class of ADFs. And on the other hand, on the other side, we provide the translation from ADF plus in general, from attacking ADFs to SETAF. Our translation, again, is based on minimal rejection conditions. The situation where we have each accepting condition, all of its subsets will also accept the statement. And once we have a rejection condition, all of its supersets will reject the condition. And we can show, we showed in the paper, right, that for attacking ADFs and no redundant links, our translation and Polberg's translation are really both bijective and each other's inverse. We can compose the translations and retrieve, if we just get from a SETAF, we can translate into an ADF. We will obtain an attacking ADF with no redundant links, as we prove. And then from it, if we use our translation back to SETAF, we'll get the exact same SETAF we had before. And also the other way, if we start with an attacking ADF, any attacking ADF really. Oh, no, there's something, yeah. We need to start with no redundant links in this case. If we get the translation itself could be done from ADFs, from attacking ADFs with redundant links, but for the bijection to hold, we need to have no redundant links. So if we start with an ADF with this characteristics, right, being an attacking ADF with no redundant links, and we go to setups using our translation, then we apply serious translation, we'll retrieve the same ADF you have in the beginning. So as a composition of those results, what we get is that SETAF corresponds precisely to this class of ADFs, which are the attacking ADFs with no redundant links. To the point where the semantics in both translations, in both ways, they just coincide. We don't need to map models from one to the other. There's simply a coincidence in this case. So this is what I had to share with you. Thank you very much.